Hi, I'm Chris Jones, and this is the talk today for the IUVA World Conference on Design, Simulation and Testing of a Portable UVC Air Sterilization Unit. I was supported by Ritesh Gupta, Andy Glenn, Thomas Stelmach, and Kishore Ramaswamy for this work, all working together. So where was this about? So I'm a simulation engineer primarily with about 15 years experience, including some irradiance and optical work, but primarily flow. This was the first UV project that I'd worked on. Myself and the team were brought together under Helpful Engineering as part of an open source project to produce a PAPR or a air sterilization unit, along with a lot of other people, I'm sure, working in the efforts to help with COVID. We're a bunch of volunteers located all the way around the world and coordinated entirely on Slack. We varied from 2 to 20 members with about 5 key people involved, of which I was the lead technical engineer. We had partnerships with Stanley Electronics, ANSYS, Porex Technologies, Sandia National Labs and Emory University to help with some of the more difficult work, as well as discussions with technical experts across the world. And thanks again to Andy, Thomas, Kishore, and Viral for help in the work that's been discussed today. So in the end, our solution was the device on the right, which is a portable air-powered respiratory device. It's positive air pressure with silent fans. It deactivates more than 99% of coronavirus as a fan with a 60-liter inlet and a 5-hour battery life. But to actually get to this point, and the main part of the speech is how we actually produce this in both design, simulation, and finally validation. This is an open source design, so if any of you are interested for more information or to use the device, please get in contact. So the actual functional prototype, this is what I'll be mostly covering. We started off with a very kind of basic thing, which was, okay, we need to irradiate a amount of air to sterilize for SARS-CoV-2. So the way this was looked at was we had to design something, simulate it, so iterate and test. This was all carried out during a lockdown period across the world in early last year. We also wanted to be a simple design with minimum complications to make prototyping and simulation easier. It also was to allow us to have a very simple device that would work as an air sterilization unit for any other requirements as well. The key components were the lamp, which was supplied by Stanley, which was 1.1 watt UVC CCFL. There was also the reflective walls, which is using expanded PTFE from Porex, and then the air manifold and the overall flow holding and airflow manifold, which was 3D printed. The idea was to find out what the UV dose of this was for a 30-liter output, with the idea that it would reach a 99.9 or 3-log reduction in for SARS-CoV-2. So to start with, we actually had to design the item. This was carried out primarily with CAD design based on some simple hand calculations of UV intensity, reflection reduction, and the volumetric flow rate. And the key aspect of this CAD design was to keep it simple, buildable, and make it easy to actually produce. We also had to do a bit of part testing to actually get the values for the simulation. So this included establishing the lamp efficiency, or what the actual irradiance was, the optical testing of the material properties, primarily the expanded PTFE. From this, for example, the base PTFE that we started with from McMaster Carr showed very low results compared to academic and kind of general expectations, whereas the expanded PTFE much more closely matched the expected values. This was kind of key as we progressed through the simulation and the testing. So we started off in the design journey with an LED-based design, and then complex quartz, and then more complex manifolding, doing a 2-way inactivation. And then with the idea of simplicity in mind, we ended up with the design on the right, which is a simple flow manifold to keep the UVC within the chamber, as well as a lamp and a reflective or diffused reflective outside. So how did we actually work out how much irradiance we're doing with this. So we were supported by ANSYS in doing optical simulation using SPIOS. So we initially used some hand calculations based on pure diffuse reflection, but this ignored some aspects like the quartz specular reflection and refraction. We used this SPIOS simulation combined with the volumetric flow rates to give us that gave us expected residence time for some simple dose calculations. The material properties were based on academic papers and Porex's testing, and we used these ray tracing simulations in SPIOS to perform very quick design turnaround. So we went from the design in the top left, which was shorter, updated that, looking at using a quartz tube to protect from any possible breakage of the lamp, to the final design, which we expected to give us the correct final dose. So from the optical simulation, which was carried out very quickly, we then moved into a flow and combined simulation. So we were supported by Thomas at ANSYS. This was a flow simulation using K omega turbulence and optical simulation using discrete ordnance radiation model. This was combined with one-way DPM particle tracking and a custom programmed UDF to integrate the UV intensity over the particle's lifetime. From this, we got the minimum dose results of about 40.5 millijoules per centimeter squared, which was pretty significantly more than we were hoping for. But this was in the perfect world of simulation, of course. There was a fairly sharp curve, as you can see on the right, showing that the dose was fairly consistent between all the particles. We took the minimum value that was present as the kind of cutoff. We did a few different design iterations, the inlet manifold and the cylinder size, to get the sufficient dose. Particularly that inlet manifold meant that you could spread the flow velocity evenly as possible, meaning that the overall flow was as consistent and there was no shortcutting where something would get a lower dose. The final simulations also included the inlet and outlet piping required for the validation, which actually showed us some short circuiting because of this manifolding issue as well. So these two images show the variance just from that flow manifolding. So these are showing the particle tracks as it passes through the chamber, with the irradiance reducing as it increasing as it goes through. As you can see on the left, it's pretty consistent across all the particle tracks, whereas on the right, because of the induced turbulence and flow short circuiting, you actually get a lower total result. So from this flow and combined simulation, we actually had to build it. So CAD and simulation is all great, but you actually need to test it. So we built it in lockdown in the UK using consumer tools in my house. There was the CCFL lamp supplied, and then it was all kind of built, pushed together and sealed up with manifolding pieces to match the lab equipment. So with great thanks to Sandia National Laboratories and Andy Glenn over there, we actually were able to get this functional prototype tested using a surrogate MSR2 virus. So from this, we could actually get real approximations of what we expected the dose to be. And this allowed us to see if the simulation was correct. We knew that the result would always be lower than the simulation because of differences in the real flow, the differences in materials, and particularly for us, the lamp heating actually had a big impact on the total irradiance. From this, we tested on a couple of different flow rates, 20 and 30 liters per minute, and we got 99.9 or 3 log reduction at 20 liters and just under that at 30 liters per minute. So this was pretty great, especially for a team where this is all our first UV project. So we were very hopeful, but it was great to actually see the results in the end. Simulations are always great, but it's always great when you see the final numbers come from a real test. Some of the things that this really showed was that there was some standard practice for testing in terms of aerosol size, particle counts, and so on would be very useful for being able to benchmark devices against each other and accurately kind of see what we're actually getting. And we actually also think that we found that the reduction from the simulation was mostly dominated by the specification divergence from the simulation results. Additionally, getting a MSR2 result, correlating that to a real dose is we found quite difficult, despite discussions with quite a number of people. But some industry research or just some basic standards applied in combination with perhaps aerosol size particle counts for the industry would be very useful, we think. The results of this gave us some very clear requirements for the simulation, and that was then input into the final consumer unit. So in conclusion, this the design and the functional prototype allowed us to actually design the final consumer device. The simulation results showed us a pretty good, at maximum we'd expect a 50% reduction, so we used that as a basis for the design. So any simulation results we got, halved those and said, okay, that's what we're actually going to get. It also showed a great use of simulation to allow a team of engineering experts within the field to actually develop, design, build, and test a device. We found that using a simpler benchmark can be really useful as a first step. And one of the things that we found as well is that it would have been ideal to use a complex multi-physics optimization tactic using, say, Latin hypercube or response surface modeling. But in the end, due to the times required, it was still best handled by a skilled operator who could actually see there and change design in a more targeted way. So in the final consumer design, you can see the simulation here. So it's designed for 60 liters per minute at a 10 millijoule per centimeter squared throughout the lifetime of the lamps and everything else. It's designed for easy doffing and donning to allow eating and do your working life, as well as being cleaner without autoclaving. So this is now being released as an open source design for people to take and either build themselves or use to develop new items as well. Thank you very much. Please let me know any questions and either email or contact us at UVisor if you have any further questions as well. And now I'll be taking questions from the conference audience.